Quantum mechanics. So from the blurb, I pitched it in between physics and philosophy. I want to get onto interpretations because I think that's the really interesting thing. And it's where the really interesting edge of science is. In a sense, you can just do quantum mechanics without worrying about the interpretations, and it works. And we've got computers and all sorts of crazy devices. But I think the really interesting thing is what we understand about reality through that, or the different ways you can understand reality through that. And I want to have a look at the different interpretations to give you a bit of a heads up before you get to university. When I went to university, it was very much taught in one mode, which was the Copenhagen interpretation, which was just you do the calculations, you don't really worry what's going on in reality. And I found it extremely frustrating. I got into the Broglie-Bohm interpretation, and it was like, oh, that's what it means. And that really switched things on for me. So I'm going to try and give you a bit of an introduction. It's not going to be like a hardcore mathematical course. I'm going to do as much of the physics as we need to get to interesting interpretations. And then I'm assuming a lot of you are doing physics anyway. Anyone not doing physics at uni?
Oh, at uni, no.
At uni? No, but you're not even doing physics now?
I'm just really interested in,
Okay, so you're more interested in the philosophy side of things?
by all means, go physics heavy. Like,
Oh, okay. But I'm going to try and cover a lot of the physics just to get enough into the philosophy side of things as well. Okay? But you're not doing...
I do the A level more for you, but I'm doing philosophy.
So you're...
Yeah.
The philosophy side of it is interesting. Yeah. Okay. So we'll try and cover a bit of both. And some of you who have done physics, there's still a bit of quantum on the course, yeah. But I think next year they're going to move to different course, so they're not even quantum on the course next year. But it's remarkably interesting. Okay. Now, breakdown of classical physics. It's started with, anyone know what this picture represents? Physicists?
Just the classical model of light.
No. Do you see what it is? It's got a rough inside. It's got a little hole that something's coming through and knocking around inside.
Internal reflection?
No.
It looks like light just bouncing.
It is. It's light bouncing around. What eventually, if the light bounces around enough, what's going to happen to it? It might really. It's very unlikely. How many times will it bounce around? What happens to light if it hits a surface? Some of it gets reflected, but
It loses energy.
some of it's going to get absorbed. Eventually, if you have a cavity, your energy will get absorbed. And there's going to be an equilibrium between energy absorbed by that surface and energy that actually escapes through the hole. Okay? You do measurements on that hole, the radiation from that hole, and you find out it has a very smooth spectral shape. Anyone know what it's called? Black body radiation. Absolutely, that's what I'm getting at. So it's completely randomized. Now, if we're a classical physicist, we would look at that cavity and say, right, we can work out the modes that are available in that cavity. There's an equilibrium between the energy being absorbed by those walls and the energy being emitted by those walls. Okay, and in that cavity, there's a number of modes, and the number of modes per unit frequency, per unit volume, you can work out with classical physics is 8 pi frequency squared over speed of light squared, or speed of light cubed, sorry. And for higher frequencies, you can just see visually, you can fit more and more modes into the cavity. Okay, so if you go up to infinite frequencies, there's infinite modes that you could fit in there. Okay, so just from the classical theory, you would predict that there would be more high frequency radiation. Okay, and that's what Rayleigh-Jean's law is. It's the prediction that you get more and more modes as you get higher and higher frequencies, but that would predict that we would have infinite energy coming out of this little hole. Okay, which is obviously a major breakdown of classical physics.
I don't get like, how does that show it's infinite energy?
area.
So if we go back, as you,
Sorry,
it's okay. What's your name?
Adam.
Adam. Welcome, Adam. Okay, so we're just looking at the breakdown of classical physics with cavity radiation or black body radiation. We're looking at the number of modes of radiation that can fit into a box, basically. And if you imagine the number of waves that you can fit in here at low frequencies, there's only so many modes that can fit. Okay, so you can have a single mode between this point and this point if it's a really low frequency, but if it gets lower than that, it's going to cancel out. You're not going to be able to fit really low frequencies in that box. But as you get to higher and higher frequencies, you're dividing up the space into smaller and smaller chunks. So there are more modes that you can put energy into. Okay, and classically, if there's a mode of vibration or there's a state that energy can go into, energy will divide equally all across those states, classically. Okay, so classically, it would say that, okay, there should be the same amount of energy in this mode as in the really high frequency mode. But the higher and higher frequencies you go, the more and more modes you can fit in. So there's actually an infinite number of modes as you get higher and higher frequency. Is that making sense, Rickle? Yeah. Okay. So you get to this prediction of the Rayleigh-Jeans law. So here's the wavelength is reducing. So that's obviously the frequency is going up. So we're getting smaller and smaller, so it can fit in more modes of that wave into the box. And obviously this prediction gets worse and worse the higher in frequency you get. The lower wavelength you get, the higher frequency you get. Massive breakdown between reality and the classical prediction. Now, Wien had an approximation for fitting this curve. He fitted a formula that worked better. I didn't really have a physical idea of why it worked better. It wasn't, so I flipped this around. This is frequency now rather than wavelength. So this is my Rayleigh-Jeans law. It goes off to infinity at high frequency. This is now the short wavelength. Short wavelength, high frequency that way. So it blows up before it gets to the ultraviolet catastrophe around here. But in this region, Wien's law fits fairly well. Okay, just an approximation to that. Neither fit the data perfectly. Wien's law fits better at low wavelength, and as in that last diagram, high frequency. Rayleigh-Jeans law fits at low frequency and high wavelength. This is now wavelength times the temperature, and Planck basically did a fit. He did it mathematical juggling between Wien's law and Raleigh's law, and got a line that fitted the data. Agrees with Wien's law, where Wien's law agrees with Rayleigh-Jeans law, where Rayleigh-Jeans law, and he matched it up.
So when you say that, what you're saying is that for every frequency emitted, they basically found how much energy. For every frequency, they found a relationship which said how much energy was.
Yes, this is the energy emitted at that frequency. Yeah, to some scale. Okay, and this is the fractional deviation from reality. So the reality is Planck, that fits the data. Wien's approximation deviates when you get up to high wavelengths, low frequencies, and the opposite for Rayleigh-Jeans. Yes, John.
Confused as to why it doesn't follow Rayleigh-Jeans approximation and it goes back down towards the end of the previous graph.
This one,
Yeah.
it does. It matches there.
No, I'm on the other side of it.
Because I flipped it. This is frequency.
Yeah.
This one is wavelength.
Yeah, so why at the lower end of the visible spectrum, for example, does it head back downwards?
Why doesn't it go backward downward?
Why does it go down? So
Why does Planck's?
Yeah.
So Planck combined Wien's approximation which does go down.
Oh,
So mathematically, he combined the two
Yeah.
and got an equation that worked.
Okay.
Okay, so you had the classical theory that was based on classical understanding, and you had the approximation that was a fit to the data, and Planck managed to marry the two and get a better fit to the data that actually reveals something about the underlying physics. So if we compare, again, there's Rayleigh-Jean's law that goes off to the ultraviolet catastrophe, and Planck's law, which agrees with the actual data. Okay, so Planck's law is correct. And now, what does it tell us about reality?
Since Planck's law is still based on approximations and an incorrect theory like the classical, so surely Planck's law is also an approximation.
It turned out not to be. It turned out to be as correct as we. It's just, pardon?
Isn't that quite likely?
A lot of discoveries are lucky, yeah. So if you have a mismatch between data and theory, one of the first things you do is just fit lots of curves to your data, and then you try and go towards theory that way, or you take the theory and try and predict the results and get a curve. And it's effectively what Planck did. He had both those approaches, one from the side of data and a curve fit, and one from the side of theory. And just with a better mapping of those together, it generated an equation that really fitted the data really well. And then that brought up the idea of quantization, which we'll get onto. And then that took on a life of its own. And there was other proofs of it and led to quantum mechanics. But this was the first crack in classical that led to quantum. Sorry, Anish, you had your hand up.
I was just gonna try to answer your question.
All right, do you want to go?
So does Planck's law predict there's basically a maximum energy? So there's got to be maximum frequency.
Which does
Planck's-
Planck?
Yeah.
It's not quite that there's a maximum. We haven't got quite there, but that
So there's a finite.
the higher, effectively, that the higher frequencies are somehow less probable. Okay, so you're now bringing this idea of probability into it. Not everything's equally probable that can happen. There's some kind of probability dampening on this ultraviolet stage. So here we've got classical. Here we've got the Planck law with this, looks like a decay term. It's got this exponential. We've got Planck's constant in there times the frequency. And if you expand this out with a series expansion and you take the limit in low frequencies, for low frequencies, the Planck's constant times the frequency is very much less than Boltzmann constants times the temperature. So these components will be small. So at low frequencies, Planck's law tends towards Rayleigh-Jean's law. So mathematically, they match up at low frequencies. So low frequencies, Planck law agrees with the classical Rayleigh-Jean's law. Now, what does that say about the modes in the box? Okay, so here we've got our radiation modes in a hot cavity. Really good test of quantum theory. So classically, probability of occupying all modes is equal probability for all modes. And we end up with giving each mode average energy of Boltzmann's constant times T. That's just the energy partition. We give them all equal, we end up with the ultraviolet catastrophe. Quantum says the higher energy modes are less probable. It's less probable that these will be excited. So we get this correction, and not all modes get equally assigned energy, and we fit the actual data. Why higher frequency modes get assigned energy less probably is still an open question, but that's where quantum mechanics started, and we have the death knell of classical physics. Okay, so here's from our power law, Planck was correct. The next bit of information wouldn't have been as much of a surprise if we were frogs. Frogs, or at least some frogs, can actually see individual photons. Okay? If it gets dark enough and you fire a single photon at a frog, it will be able to detect that in its eye and be able to respond. There's the equivalent physics experiment that was effectively this in a laboratory that Einstein used for the next piece of the puzzle, and physicists should know this. Photoelectric effect. Absolutely. Okay, so we've got electromagnetic radiation coming in. It hits the frog's eye or the zinc plate or whatever, and it knocks out electrons. They're collected and we can detect them. Okay, now, remarkably, you have to revert to the particle model of light to be able to explain this phenomenon. And that's what Einstein did. One of his key papers in revolutionizing the whole of physics, he just came up with special relativity, and he also came up with quantum mechanics effectively. If you change the frequency of light, if you reduce the frequency of light, so you're increasing the wavelength, less and less energy in a photon, you come to a point where no matter how intense the light is, there's no emission at all. Okay? But if the light is high enough frequency, you can still detect a current, even if it's really low intensity. Okay? So we look at the graph. Here's the frequency of the incident radiation. It's completely independent of the intensity of the light. Light below a cutoff frequency, no matter how intense it is, even if you're melting that plate, you wouldn't get electrons freed from it. Okay? So the fact that this plot was not dependent on the intensity implied the interaction was particle-like. Okay, so if the particle doesn't have enough energy to kick out an electron, doesn't matter how many you throw at it, no electrons get kicked out. But even one particle, if it has gotten high enough energy, boom, it can kick out an electron. Okay? So it gives all the energy to one electron and ejects it with that energy minus a bit that it takes to escape. So you can now think of it's in this little potential and it needs a bit of a kick to get out, this little particle of my electron. And it doesn't matter how many kicks I give it. If it doesn't get over the barrier, I'll never see it. But just one kick that's big enough and I can detect that electron. So for instance, with sodium, this linear increase shows the electrokinetic energy, shows whatever is ejecting them is proportional to frequency. Okay, so energy is proportional to frequency. And you can determine the energy of the electron if you put a retarding electric field. So you're pushing away the electron from the collection plate. There's a certain point where it won't be able to reach and be detected. So you can detect how much extra energy, additional to getting out of this potential well, the electrons have. Okay, and that straight line, if you've got the depth of the potential, that little bit of energy, then the rest of the energy from the photon just goes into the electron. It's just energy is proportional to frequency that you've measured of the light, and that all gets put into the electron. All making sense? Okay, good. Next piece of evidence is from energy levels in atoms. So for ages, we knew that the flame test could differentiate between the atoms of different elements, but we didn't know why. But the emitted radiation comes in these chunks. You can work it out, and you can basically get a fingerprint for different atoms. And these kind of energy levels that are in the atoms, another bit of evidence that just can't be explained classically. There's something else going on here It's something that is dividing up the energy that's getting out of these atoms into chunks. Okay. Next bit of evidence. So you've got the Planck law of a black body for a star, but you've now also got absorption lines and emission lines. So this opened up a whole load of stuff about stellar and solar chemistry. So you could actually see the same stuff as out in the universe as we could see on the ground, and you can map it. Okay, now we have another interaction between photons of light and electrons. You can scatter various photons of electrons, and you can measure the frequency of the photon afterwards. You can measure the speed of the electron afterwards. And for different angles, you can show that the energy gets shared out in different ways. They're basically acting like particle collisions. At 0 degrees, you've got all the energy in the photon, none in the electron. 180 degrees, most in the electron. Electrons heavier, still some in the recoiled photon, and then back down to 0 at 360 degrees. Okay, so they're acting like particle collisions that share out the energy. Okay, what's the next step? So if radiation can be described as a particle, then maybe, yeah,
Particles can be described as waves.
as a wave. Okay. So we know that radiation definitely is waves. Young's double slits had already concluded that debate, showing that they were waves. But if we do the same experiment with electrons, actually this is jumping ahead of ourselves slightly. You can do the same experiment with electrons. But before we got to the experiment, obviously we can understand these particles that were discovered during the particle model. De Broglie hypothesized if photons can be described as particles, what about the matter? Can we describe that as a wave? The fundamental idea of his thesis was the following: the fact that following Einstein's introduction of photons in light waves, one knew that light contains particles which are concentrations of energy incorporated into the wave. This suggests that all particles, like the electron, must be transported by a wave into which it's incorporated. My essential idea was to extend this to all particles, the coexistence of the wave and particles, discovered by Einstein in 1905 in the case of light and photons. Okay, so you took the idea and applied it to matter. Then with every particle of matter, the mass m and velocity, there's a real wave that is associated in some way with this particle. And this wave has a wavelength related to the momentum by this equation. So we've got de Broglie wavelength is equal to Planck's constant, there's Planck's constant again, over p, which is the momentum, or the mass times the velocity in this case, and the relativistic part of that for working out the momentum. Okay, and let's go back to this. This was then tested with electrons, and electrons were shown to diffract. And they hit the screen, they appeared as points, but when you built up enough, you could see the wave patterns. Sorry, Adam.
Is wavelength relative to that? Since the de Broglie wavelength is a Planck constant over momentum,
Yep.
velocity is relative.
Yep. So,
wavelength can also be relative.
Pardon?
Wavelength can also be relative.
So wavelength is inversely related to momentum. So the higher the momentum, really high energy particles, then you've got a really short wavelength. If you've got really low momentum, you get a really...
But then if the particle is moving, like not moving relative to you, what would that affect its wavelength?
Yes, the detected wavelength, yeah. This would be relative motion. You're imagining
Yeah, just relative.
if you have... Yeah, so if you stuck your electron diffraction experiment on a rocket, you get up to half the speed of light, and then you're cruising along at half the speed of light, you do the experiment again, it would give the same results.
Okay.
Yeah, so the momentum in the rest frame of the detecting apparatus would be the relative momentum. Yes, it's relative. Okay, and then experimental, this was then proved. So the theory set the stage for the experiments. At this stage, it's supported by Einstein. It's confirmed by the electron diffraction experiments of Davison and Germer. And then Schrodinger took that and generalized it with his wave equation, which we will look at on Wednesday, which put the wave nature of particles and light into a formal mathematical structure underlying the wave nature. Okay, brief introduction, even briefer one. So quantum's a discrete quantity of energy proportional magnitude to the frequency of radiation it represents. So we've got the idea that their frequency and energy are related. Analogous discrete amount of any other physical quantity, such as momentum or electric charge. So we've got discrete bits of things, but the weirdness comes into how you marry up the ideas of the wave nature and the particle nature, how they map together. And actually, the wave function that Schrodinger came up with, in some ways, it looks very much like a normal classical wave equation, but there's subtle differences that have big implications, and we'll look at those, or start to look at those on Wednesday. Okay. I think hopefully I've moved some of these into the air and covered some of these that non-physicists wouldn't have met yet either. And we'll carry on Wednesday. Okay? Thank you very much. Do post anything, discussion, questions, comments on the classroom as well. And there's a classroom code. Did you not get an email for the classroom code? That's the old one. Okay, so that's the new classroom code. And there's a couple links on there as well. Quote from Feynman, and also a good introduction textbook. So like a university entry level textbook. It's quite good. That will just cover some of the stuff I've done today again, a little bit more detail. It's got some problems at the end of the first chapter. We haven't got quite through all the material in its first chapter, but you might want to have a look at some of that.
Yes, sir.
Very welcome.